It is chapter 5, integrals. In this chapter, we first develop a method called integration, which is the definite integral. The definite integral is the key tool for calculating areas and volumes in calculus. And later on, we'll show that the process of computing definite integrals is closely connected to finding anti-derivatives. The connection is summarized in the fundamental theorem of calculus. Okay, let's go to section 5.1, area and estimating with finite sums. And here, we'll begin with the area problem. An area can be found quite easily if it is some good shape, like a rectangle and triangles and circles. But once the shape is general, then it's not easy. In this example 5.1, suppose we want to find the area of shaded region R that is made with the curve y equal 1 minus x squared and x between 0 and 1, and now here underneath the curve. Okay, so we cannot find the area by using simple technique, and now we try to approximate it, the area, with a finite sum of rectangle areas. Let's look at these pictures. Okay, now we want to find the area underneath the curve. We, to do that, we here partition the interval between 0 and 1 with 2 subintervals. Then for each subinterval, we try to measure the rectangle area. Right now, from here to there will be 0.5. Now, for the height, we are using left endpoint of value of the curve, so that that'll be 1. So we consider this rectangle, and we can find the area of this rectangle quite easily. For the next, the other rectangle, we can find the area easily. Then the sum will approximate the area, but it's not quite accurate. How about we have 4 subintervals? Then now each rectangle area will be summed to approximate better than in this case. If we try to take more subintervals and number of subinterval grows to infinity, then probably the summation will become a much better approximation of the original area. That is the idea of finding area. Okay. Here, algebraically, we can find the approximation. For this case, for subinterval, now each subinterval bottom length is 1/4, and left endpoint value is now in the beginning f of 0, f of 1/4, and 2/4 and 3/4. So the values are 1 and these values. So that is a summation of rectangular areas, and it becomes 0.78125. Now, by using a computer program, we can check here quite easily. And here, f is defined in this way, and 1 minus x squared, and beginning point, end point. Now, I is moving from 1 to n, and number of points will be gotten 2 to the I, so that once I is 1, then n is 2, I is 2, then and now n is 4, so that twice more subintervals will be chosen, and corresponding the horizontal interval length. Okay, and then now here x is now x values, and at x the y values will be made. Now here left endpoint value is start from 1 to the last one. Right now here that is from 0 to n and dx. That means that here in this case that is first one, second point, third point, fourth point, fifth point, so that if you are using left end point, then all you have to add this up to that one, right? So here in program, the y value is from 1 to the n minus 1. That means exclude the value at end point right now. Okay, and summed n and dx, exactly like this one, we are adding the left end or values of function and multiply dx 1/4. And that's a left sum. And we print out for each case here the values. The true value is 2/3. We can check it, the accuracy of that sum. Let's go to program. Okay, is Matlab, but you can use here Octave is a free alternative to Matlab. Okay, here that is the program, and right now this line will give you also the error, so it is included at the end right now. Okay, let's see a little bit larger. Just a moment. Okay, so here right now, oh come on. Okay, so here one more is now error is printed out, absolute value of left sum minus 2/3. Okay, we execute it by pushing now F5. Then you can see here now result. Okay, that is what you can see from the lecture note. These are extra one error. Look at here, error is in the beginning 0.2 and around 0.1 and about half of that and so on. So you can see in general error becomes halved, and by choosing twice more points, so it is called first order convergence. In this way, if you are choosing more subintervals, then the area approximation becomes better, and more accurate solution can be obtained. Okay, now the early example is along with a left endpoint. Now you can use right endpoint values. For these 4 subintervals, you may try to use here for each subinterval right end value and try to get height. So this rectangle area will be contributed to the summation. And so in this algebraic expression, now quarter is bottom length, and for this subinterval, we are using for the height and f at 1/4. So the area is computed from this one, and so on. So it is now total summation is less than 2/3 because we are missing this now the area. Okay. Now also you can use midpoint values for each subinterval. try to get mid value and try to get the area by using the height from midpoint. So it looks like much better. Some are missing, but some are added so that they cancel out, so that it can be better. Okay. So if you are using midpoint values, then now it's much better than the one-sided the point values. The true value is 2/3, so it's much nearer to 2/3. Okay, by using computer algorithm, you can easily check that here now left sum, right sum, mid sum are made and printed out for each n. N is now twice increased each time, and you can see that here for mid sum right now is way better than the other two, and the true value is 2/3, so that it is approaching much faster way. In fact, these two are first order convergence. That means that if you make the subinterval twice, then the error will be halved. But for this midpoint rule, if you make the point twice, then the error will become quarter. So it is a second order convergence. Now, for the example, using left endpoint values is basically upper sum approximation. Now, right endpoint value is the lower sum approximation. Okay, for this example, let's go back to that one. And now for this example, we are using right endpoint, then it's a lower sum, because you can use left endpoint or right endpoint, but if you are using left endpoint, then it is a sort of upper sum. Eventually, upper sum will be larger than the real area, true area, and lower sum will be smaller than true area. Once the function is increasing, okay, for example, now that one is decreasing, but here, once the function is increasing, then for each subinterval, here, if you're using right endpoint value, then it's upper sum. If you're using left endpoint value, then it will be lower sum. Right? Okay. So because this is a decreasing function, now left endpoint will be upper sum, and right endpoint value will be for lower sum. Okay. Okay. Now, these summations can be manipulated algebraically. Okay, in this example, now we are using rectangles of right endpoint values to estimate the area under the parabola y equals x squared from 0 to 1. Okay, the true area is 1/3. Now, once you try to get the right endpoint summation, then now if you make a partition n subinterval in this picture, we try to get 8 subintervals, so that first point is in 1/8 and 2/8 and 3/8 and so on. If we choose general n subinterval, then right endpoint for first subinterval will be 1/n, and next one is 2/n, and so on. So the last one will be 1/n, which is 1. Now the function is y equals x squared, so that right sum will be 1/n, and that is now interval length, and at the right endpoint of a first subinterval, and there's 1 over n, and the function is x squared, so that 1 over n squared. From second on, we have this height, and so on. So if you add them and manipulate here algebraically, then 1 over n squared will come out, and now the square sum is the limit term. And for this one, you learn in the next section the quantity, so which is n plus 1, 2n plus 1 over 6. You learn it, that one in the next section. So along with that, you can expand it this way. And here, as n goes to infinity, you can see that these two terms will approach 0, so that there is 2 over 6, which is same as 1/3. So limit value is 1/3. And also you can see that that is now half. Okay, this term, if n is larger and larger, larger, then this is way smaller than that one. So that this is a major error term. So once you make n twice larger, then this term becomes half. So you can see from this example that now this convergence is first order. Now this program is now the Python, and by using NumPy, and you can print out the quantity. Now number of interval is 2, 4, 8, and so on. Now for the function y equal x squared, this right sum is print out in this way. It's approaching to now 1/3. Okay, 1/3, which is 0.33, like that. It's approaching to 1/3. You can see quite easily, and convergence speed is first order. Okay, this is the first part, and I'll see you in the second part. Thank you.